All right, nice to see everybody on Zoom. We're, I think, mostly settled here in the room. Thanks, everybody, for spending your lunch hour with us. This series is a collaboration between the ADRC Research Education, the AD and the T32. So we're really happy to bring all of these scholars together to share with one another about their work and career path. We encourage you all to connect with one another and share your learnings, and hopefully even some new collaborations will come from this series. Today we have Dr. Sundermann speaking. I'll let her introduce herself and her work. And yeah, without further ado, thank you.
Thanks, Emily. Hi, everyone. Thanks for being here and on Zoom. I think I know most of you. For those of you I don't know, I am an associate professor in the Department of Psychiatry, cognitive neuroscientist by training. A lot of my research, I'm in the cognitive aging Alzheimer's disease research space with the big focus on sex differences and female-specific health factors that relate to brain health and Alzheimer's disease risk. I was fortunate enough to be a REC scholar in 2020 to 2022. I used that opportunity to kind of play with a new research avenue for myself. And that is in natural language processing and how that can be used as an early predictor for Alzheimer's disease. So the REC program worked out really well for me because it allowed me to kind of experiment with this new area with pilot funds and get data and team up with people, you know, both at the ADRC and other computer scientists in that particular area, and find new collaborators, which was really great for me, and I've been pursuing it ever since. So I would say it was a success and something I still very much interested in. So with that, I'm going to go ahead and share my slides. Hopefully everyone can see that okay. Okay, looks good. Okay, so I'm going to be talking to you all about my REC project, which was the potential of natural language processing as a low-cost, non-invasive marker of early-stage Alzheimer's disease. Okay. So it's well known that even in early Alzheimer's disease stages, you see deficits in language processing, and that's including on tests of verbal fluency and semantic retrieval and naming. These changes in language function result from pathology that develops in brain areas involved in memory and language, so temporal lobe and frontal lobe. And this pathology then leads to difficulties in retrieving word meanings and associations. These deficits in language processing can result in changes to the timing, the acoustic, and the linguistic elements of speech, including things like the number of pauses someone takes, the length of a pause, their overall language output, voice amplitude, and sentence structure. Those are just examples. So these more subtle changes in language and communication may be apparent years or even decades before we see impairments on clinical tests. So that means that language alterations have the potential to serve as an informative and earlier marker of cognitive dysfunction by offering this more subtle and granular information than just whether one meets an impairment threshold on a clinical language test or even other standard clinical tests. So more and more attention is being paid to computerized analysis of spoken language, which is known as natural language processing, or NLP. And this allows for the automated measurement of elements of speech that go unmeasured in conventional language tests and can't be perceptible really to a clinician's ear. So a more well-known example of speech alterations as an early Alzheimer's marker was from Brian Butterworth, and I just find this interesting, so I always put this in my slides. He was a professor of cognitive neuropsychology at King's University College London, and he studied speech errors, speech processing, and pauses. And Ronald Reagan was running for re-election in 1984, and he was listening to his re-election campaign and had some serious concerns that he might be on an Alzheimer's trajectory based on his speech and his re-election talks. So he actually published an article about this in the Sunday Times, and this was 10 years before Ronald Reagan was formally diagnosed with Alzheimer's disease. So there's a number of different tasks that have been used to elicit language. The more popular ones have been a picture description task, which is where the participant is given. Oh no!
Make sure that your screen is shared with.
Okay, so here we were. So yeah, these are examples of tasks that can be used to elicit language. A very popular one is the picture description task, which is on the left. This is a very commonly used picture. It's the cookie theft picture from the Boston Diagnostic Aphasia exam. Also commonly used is just what we call autobiographical interview. So you just ask somebody, you give them a topic to talk about. Maybe it's a memory of a certain event in their life, or a typical work day, or the last dream they remembered, anything just to elicit speech. Some studies will record certain neuropsychological tests that elicit more language, like a story recall test or even verbal fluency, and then use those for natural language processing. And these types I mentioned so far are considered spontaneous speech tasks, but there are also read aloud tasks in which the participant simply reads scripted text on a screen or on a page. And so these tests are more rare in the NLP literature, but they're thought to have an advantage in that they are a more simplified task that that does not afford the flexibility that spontaneous speech tasks which provide, which may allow older participants to compensate for language production deficits using different tactics. So read aloud tasks obviously don't assess the higher order cognitive function tasks of like concept formulation and structuring your sentences, but it may allow for a purer and more precise measure of deficits in the more basic temporal and acoustic features of language production. Okay, so there are several language outcomes or parameters that can be measured, and the panel of outcomes often are different across studies, which has made it difficult to compare results across studies. But for the most part, they tend to fall into the categories of acoustic, temporal parameters, speech production, and syntactic complexity. And these I made them overlapping Venn diagrams because, of course, the outcomes in one category can often influence the parameters in another category. There are often hundreds of parameters that can be measured. So I just put some examples here. So like acoustic temporal parameters might be pause ratio, pitch, variability in rhythm and pitch, speech rate, articulation rate. Speech production would be things like number of words and number and length of silent and filled pauses, length of utterance, number of uninformative words. Syntactic complexity would be like speech chunking, proportion of words and sentences, number of embedded clauses, syntactic errors. Yes. No, that's just an error. You're right. I should have the intersecting triangle for all of them. Okay. So there are several advantages of NLP as an early marker of Alzheimer's related changes compared to gold standard clinical test batteries. Obviously, it's low cost. It's non-invasive. It's computerized, so you remove any sort of time burden or human bias or error. The ubiquitous nature of language and the ease in which it can be recorded and analyzed using AI means that it could really serve as a very widespread, scalable health outcome that's not limited to high resource settings. Natural language assessments can be easily conducted continuously, so they offer the ability to track changes over time in people, which is usually a more sensitive measure than just a cross-sectional assessment. And it offers a more stable and accurate picture of one's cognitive status than just one snapshot in time. And lastly, language, we can record language that's spoken in one's natural day-to-day life. So that can make it a more ecologically valid tool as opposed to, tests in a lab that can often elicit a stress response. And there's incredible complexity in the information you can get from it. Lots of dimensions. It can help tease apart. Just obviously, the big thing we've been talking about is teasing apart disease trajectory from healthy cognitive aging, but there are examples in the literature of how it can tease apart different types of dementia. It can tease apart different stages of disease trajectory. So there's a lot of potential. So in about it was like 2015-16, the area of natural language processing in Alzheimer's disease really started growing. And this slide is just a sampling of some of the big studies that have been published. Most were reporting the ability of language parameters to discriminate clinical AD patients from cognitively normal patients or MCI from cognitively normal. And with classification accuracy that ranged, you'd see ranges that starting at decent low 70s up to 90s. But there was also some studies that found that language parameters predicted pathological burden in MCI or AD cases, that they are able to differentiate between MCI subtypes and staging of disease severity. Okay, so what do we know? We know from multiple studies that speech alterations in MCI and Alzheimer's disease exist and can be used to help distinguish those clinical conditions. I will say, though, there has been variability in the specific parameters that have been identified by studies. So often these studies look at overall ability of this panel of language outcomes to classify, but then they look at the top predictors among these parameters, and those often differ across studies. And that has a lot to do with the fact that different parameters are studied across different studies. We know that language studies suggest that longitudinal studies suggest that language alterations track with disease severity. And linguistic parameters from both spontaneous speech and a scripted read aloud task have been related to MCI and dementia. Okay, so what we know / don't know. This is a picture of the clinical trajectory of Alzheimer's disease. Most of you probably are familiar with this, so I'll just go through this quickly. You have your preclinical stage, which can happen decades before dementia onset. And it's when you don't have any clinical symptoms yet, but there is pathology building in the brain, and you can detect that using biomarkers. And then you have MCI due to Alzheimer's disease, which is where you start to have mild cognitive symptoms, but they don't interfere with daily life. And then you reach the dementia stage where your cognitive impairment does indeed interfere with daily life. So the studies so far have been shown that we can discriminate MCI and dementia from normal controls. Question mark above preclinical. At the time, at least that we designed this study, no study had really looked at whether NLP could identify people who are cognitively normal according to clinical tests, but may be on an Alzheimer's disease trajectory due to pathology building in the brain. So we don't know if linguistic features relate to preclinical Alzheimer's disease. We don't know whether linguistic parameters derived from spontaneous versus scripted or read-aloud speech are more sensitive to early cognitive deficits. And how might linguistic features contribute to detecting underlying AD pathogenesis over and above neurocognitive testing? So with that, with the help of my team, which I'll go over, I think, in a slide or two, we designed this study with aim one was to use machine learning methods to determine the predictive value of linguistic features in discriminating Alzheimer's disease stage, preclinical AD versus MCI versus AD, and compare the most predictive features between spontaneous versus scripted speech, with the hypothesis that linguistic feature profiles would discriminate disease stage with good accuracy, and the most predictive features will be a combination of features from spontaneous and scripted text speech. And aim two was to compare the ability of linguistic features in predicting MCI-AD dementia status and biomarker positivity status over and above neuropsychological scores. So our hypothesis there was that if you add linguistic features to standard neurocognitive test scores, then we can have better accuracy in predicting AD biomarker positivity in MCI status. Okay, so my study team, this was truly a group effort. I was new to this area. I'm very thankful to Dr. Tamar Golan, who is an expert in psycholinguistics and speech production. So she was one of my first phone calls when I, emails, when I started this project. And thankfully, she was interested and willing to team up with me. Dr. Rayanne Moore, who's an expert in using digital health technologies in aging research, and she has a lot of interest in natural language processing. And this is a big computer science area. So you need the computer science expertise and the modeling to really be doing these big machine learning type models. So we teamed up with a couple people from the University of Illinois, Chicago, Dr. Natalie Pardee and Dr. Alex Lowe, who are both computer science experts. Dr. Pardee had specific expertise in natural language processing, and Dr. Lowe was an expert in applying omics approaches. And then, of course, my ADRC rec mentors was Mark Bondi, Linda McAvoy, David Salmon, Jim Brewer, and Doug Glasgow. So our inclusion criteria was pretty simple. ADRC participants willing to complete a speech task for about 10 minutes during their standard ADRC visit. This was in 2020 to 2021. And they had to be fluent in English, of course, and have a decent size computer screen. At least that was added once we realized that COVID hit, which I'll talk more about in the next slide. We excluded anyone with moderate severe dementia just because the task would become compromised due to the the burden on people with moderate severe dementia. Okay, so yeah, this study was funded like in lockstep with COVID. So we had a big COVID pivot. And we were very fortunate because honestly, like this was one of those studies that was very adaptable to remote. So it was supposed to be given in person as part of the ADRC test batteries. And we said, well, gosh, and we can just do this remotely, no problem. We'll do it on Zoom. We'll record it, and we made it part of the TCOG battery, which the ADRC had pivoted to during COVID, which was an abbreviated battery that was able to be done remotely. Our methods were a 5-minute spontaneous speech task. So we asked the participant in 5 minutes, tell me a memorable event from your early adulthood. That could be anything, a wedding, a first job, etc. And then we had them read aloud 5 paragraphs that will just appear on screen one by one. So that was the scripted language task. And then at that visit, they were also given a cognitive test battery, and those tests are listed there on the screen. And this was a time people weren't coming into the ADRC, so blood draws and lumbar punctures weren't happening, unfortunately. So we couldn't get that data, at the exact same time. But there were people who had CSF and plasma AD biomarkers within a period of time. And so we were more lenient with, linking this data with CSF AD biomarkers within 5 years, and plasma we were able to do within 1 year. This is just an example of a normal scripted paragraph. So this is what the participant would see on their screen, and this is what they would read out loud. Okay, so this was our study pipeline. So we would remotely administer language tasks to participants. Recordings would be auto-transcribed by a software program, and then those automatically generated transcript would then be manually corrected for errors. And I'll talk more about that later. And then we would computationally extract 86 language features from both audio files and their text. And then lastly, sorry, I realized that my slides are covering up, my images are covering up some text. Machine learning, we would do machine learning analysis to determine the utility of language features in predicting preclinical AD and MCI. Okay, so speed bumps along the way. Speed bumps, COVID, as I already mentioned. So fortunately, we were able to switch to remote administration, which was awesome. We were still able to do the study. Unfortunately, we got a lot less participants than we thought we would. We were shooting for like 200. We got about 91. And we also got very few MCI, AD, dementia, mild AD dementia participants. I think only really a handful. So mostly cognitively normal. And those were probably because those are the people willing to do the remote TCOG battery. So we decided to really just focus on AD biomarker positivity and predicting that as our outcome, and not so much MCI or even AD dementia. So our overall sample was 82 cognitively normal older adults, 6 MCI, and 3 mild Alzheimer's disease. We had a subset with CSF, 63 with CSF, I think collected within, I can't remember if we decided on 3 or 5 years. And then with blood AD biomarkers, we had 77 participants with those within a year of data collection. Okay, other speed bump was the auto-generated transcript required lots of manual editing. We did not foresee that. We ended up having to spend a lot of time, months, having a team of undergrads that really combed through. They had the recording and they had the auto-generated transcript, and they listened to the recording and they checked that transcript as they listened to the recording, and they corrected all errors as well as applying speech tags. So of course, you have speech from the interviewer and the participant, and all you care about is the speech from the participant, right? They were also in charge of applying speech tags. So when the interviewer was talking versus the participant. So I think I have an example. Yeah. Okay. So I put an example of a raw transcript. So I highlighted in red where you see some serious errors. So this is what we would receive from the auto generation, and as you can see, there's just some parts that are just nonsensical. So it required a lot, and I was very thankful to have a team of 7 undergrads that were willing to help out with this project and go through all of these. But it took a long time. Okay, so I'm going to show you some results. I will say that our sample size of 91 is very small for a machine learning analysis study, but we tried it anyways, and we had some findings. They weren't great. But we did end up publishing them as part of a paper that was more about explaining the data set that we have and the data that's available with a side of preliminary findings. So we are collecting more data, thankfully to the ADRC, who's willing to allow us to do that. So I'll talk more about that, but these are some preliminary results from our initial sample. Okay, so here on the left, you have all of our biomarker positivity outcomes. We were specifically looked at CSF, t-tau A beta ratio. There you had 21% were positive. CSF A beta 42/40 ratio, 33% were positive. And plasma p-tau 181 where 35% were positive. So the first thing to point out is the imbalance in the percent that were positive versus negative. So machine learning analysis, what I've learned is that machine learning really likes balance. They like 50-50. We didn't have that. So to address this, we applied different techniques and ended up with a SMOTE technique, in case anyone knows this stuff. Which improved prediction performance. But it's this stuff that I was very grateful to be teamed up with computer science people. And often their conversations about this went over my head. All experimental results were obtained by averaging performance across 1,000 random forest training test runs, which the sample was split into 80% training and 20% for testing. So these along the top, you have A, F1, and ROC, AUC. These are different performance metrics that are used to evaluate classification ability. The A stands for accuracy, and each one has its own advantages and disadvantages. So they are often looked at together to give a more complete picture of classification accuracy. But in this context, for this particular data set that had imbalance, we focus more on area under the curve values on the far right. So the feature column, this one right here. So of the 86 features, we then down sampled to a set of the most informative features and then determine the ideal set size by comparing prediction accuracy when limiting to different number of predictors. So across the board, we found that top 8 features generally exhibited the best performance across our target variables. So the ROC AUC values for the 8 feature set are bolded, and they're around 0.70, which means that on average, the model had a 70% chance of correctly distinguishing someone who's biomarker positive versus someone who is not. This is decent predictability, but it's not great in the range of ROC AUC values. Okay, this is just a figure showing you the top linguistic features associated with p-tau positivity. I'm not going to go through all the biomarkers, but it was the plasma p-tau positivity that really showed the best classification. So I thought I'd just show you this one. So the graph is showing you the correlations between specific features, linguistic features, and the biomarker positivity, with the size of the correlation determined by the color, and whether it's positive versus negative, is determined by right side versus left side of that line. Obviously, these words mean nothing to you, so I put this over here, what our top features were. Speaking rate, sentence structure, metrics, unfilled pauses and filled pauses, percentage of verbs, skewness and kurtosis of duration of speech segments. So then we next compared the ability of our model to predict Alzheimer's biomarker positivity compared to just standard clinical tests of cognitive function, to better understand whether our model may be more effective in predicting Alzheimer's biomarker status compared to our current tools. So here are ROC AUC values for the different biomarkers we looked at. And the only cognitive test that approached our language model performance was the letter fluency task, which predicted t-tau A beta ratio with a comparable ROC AUC. Was less than 3% difference from what we saw with the language. However, this test did fall short when looking at the F1 score by about a 15% decrease. And all other models exhibit at least a 10% decrease across all metrics compared to our model trained on speech. So our language model, it wasn't great, but it did better than our standard cognitive battery in predicting biomarker positivity. Okay, so future directions. So as I mentioned, we need more data, really, truly. So we thankfully, Christina and Emily and Doug and David were willing to help me out with that and restart data collection. We just started a few months ago. We have a couple of volunteers who thankfully are willing to call participants and ask them if they'd be willing to do the speech task. And we're aiming for another 90 participants to double our sample. And we're going to try a new software program for auto transcription. We've seen some papers come out saying they use this, and according to our computer science people, they say they think they will be better. I hope so. I'm crossing my fingers. So yeah, once we get all that data, we'll repeat our analysis in a larger sample. And, we can also look at baseline NLP assessment, because ADRC is obviously a longitudinal study, and they'll continue to collect data. It would be really cool to look at baseline NLP assessments in relation to cognitive and biomarker trajectories and incident MCI down the line. And also, we have not yet done a comparison of the spontaneous versus the scripted language comparison. So that will be cool to do once we have a larger sample. Fortunately, I did lead to a funded R01 for our team. Dr. Natalie Pardee is the PI of in R01, and she asked myself to help out as a co-investigator. So the R01 is the fair and interpretable prediction of Alzheimer's disease and MCI using large language models. So this is about a year in. And the broad aim is to develop high-performing, fair, and interpretable large language models to detect Alzheimer's disease in its precursor stages. So really, we're talking about AI here. How can we harness AI in NLP analyses? And how can we do it in a fair and unbiased way and improve interpretability? So I put in the specific aims down there, but I see this really as a collaboration between computer science people and clinical people like myself that can help with the interpretability piece of this. So it's just, like I said, the rec was an avenue for me to start this new research focus, and I was able to find a team and new collaborators, and it has led to this funded R1, and I hope even more in the future once we're able to get more data and leverage that for future R1s. So with that, I will thank my study team and all the ADRC psychometrists who helped out with collecting the data. And these are my wonderful team of undergrad research volunteers that did all that manual auto correcting. And then, of course, the REC program. And with that, I thank you all for listening, and I'm happy to take